Fibonacci numbers efficiently. Yeah. So I give you two parts. The first part, standard part, relatively easier. You need to compare two algorithms, both given in our notes. All right. The first one, here I give you the reference, the notes. Module 3, part C, page 1, this function. Yeah. Just a recursive, direct recursive function call. Just a few lines, a few simple lines. So you can write, let's say 5 minutes. 5 minutes, you complete that function. So simple, the first method. Second method, I'd like you to use another simple one. Module 3, part C, page 4, method 2, that one is a dynamic programming. So I'd like you to practice that dynamic programming one. But the pseudocode is there. So you only need to do a little more work, remove the redundancy. How to remove the redundancy? Remember, we use one special array, dictionary method. If the Fibonacci number is already calculated, we store in the dictionary. But because we already have those values in the dictionary, we don't want to compute it second time. So the second time when you need to use that particular value, you look it up in the dictionary. So the dictionary returns the value that you use it for computation. So that dynamic programming idea is very useful. So I'd like you, through this method, you at least think about the dynamic program. Okay? Yeah. So you get yourself familiar with the dynamic programming. Okay? The coding is very simple. These two methods, very simple. So overall, this project is pretty simple. Okay? Not too hard. But I add a little more work. If only compare these two methods, probably too easy for you. Okay? Too easy for you. So I'd like you to learn a little more. All right. Yeah. And the first method, you should expect very slow. When you test it, very, very slow. If I use this 30-second line, you just pick some input. Fibonacci f of n, right? Or f sub n, Fibonacci number, f sub n. You can try 40 something, okay? 40 something. Where n equals 40 something, you will see the waiting time is very long. 40, f of 40 something, okay? A little larger than 40. Okay? The waiting time should be more than 30 seconds. Depends on your machine, how powerful is your machine. Okay? Yeah, so you should expect waiting that long. Because when you work on computer, 30 seconds is extremely long. Right? Think about it. You sit there waiting 30 seconds. You cannot tolerate that long. All right? Yeah. But when you do experiments, for first method, extremely bad. How bad it is. Here, how bad it is. I didn't tell you how bad it is. If we use the asymptotic notation. Those students who came in late, before you leave the classroom, just let me know, check your names. All right. I haven't told you how bad is the first method here. Using this chance, let me tell you how bad it is. The first method. Why you need to wait so long? Big theta asymptotic notation. Phi to the n. Phi, you know, golden ratio. Golden ratio to the nth power. That's all. That's all. That's an exponential algorithm. This function, we know, it is an exponential function. So people call it exponentially slow. How about that? Exponentially slow. All right, yeah. So through this project, we try to feel about it. Very bad algorithm. Useless. When you have exponential algorithm, just useless. Okay? Drop it, throw it away. Even supercomputer cannot run this algorithm well. Exponentially slow. Have you heard of traveling salesperson problem? Very famous problem. Traveler salesperson problem. TSP. Very, very famous big problem. So given n cities, in some region, one traveler salesperson tried to sell products, going through all n cities. But there are so many different ways to go, right? The path. How many different paths that person can take? N factorial. Among those n factorials, what is the fastest way? Most efficient way? Which path is the most efficient way? Okay? So you can calculate the distance. Okay? Use the distance, total distance. You want to find the path with shortest total distance. This famous problem we call traveler salesperson problem, TSP. But the current known solution is exponential. Current solution, nobody can find a better solution. Exponential algorithm, that is useless. Useless. No practical. Okay? No practical. Your n cannot be larger than 20. Even n is greater than 20. That's too slow. Right? And we know 20 is not a big number. Right? 20 cities. It's not a big number. So here, just to give you an idea. How bad is exponential algorithm? Okay, so this simple project, you can understand the algorithm better. The second one, dynamic programming, we improve by removing the redundant computation. We improve it to big theta of n. That big, how big is it? Very fast. From the computer experiments, what result can you enjoy by this fast algorithm? So when you do testing for algorithm number 2, later, if I mention that or not, later as I test it, I even tested, look at how large I test the Fibonacci number. F of 10,000. N equals 10,000. That is 40 something. Here, 10,000. 40 something, 10,000. 40 something, you need to wait more than 30 seconds. Here, 10,000. You see the result immediately. Okay, less than 1 second. That huge difference. That huge difference. So from this example, you can see that big difference. Okay. For the comparison, we use the big integer. Now you know the big integer, right? Yeah. So you're familiar with that big integer. Okay. I do not need to spend time explaining big integer. You just use it directly. Okay. Yeah. But before you do that, we know the reason we use big integer, avoid overflow, right? Avoid overflow. Because if we do not use big integer, quickly we get overflow. Then the Fibonacci number we calculate garbage. Garbage, it's wrong. Completely wrong. But here, I give you another part of the problem. Find the data size that results in the overflow. Just that line. Yeah. I ask you to find that line. Okay? Yeah. Before the line, yeah, so this side. From the smaller side. Before this line, no overflow. Okay? No overflow. But after this line, yeah. This line, there must be some number. Okay? Must be n number. Okay? And overflow. And O. Okay? Overflow number. After this line, then you have overflow. Okay? You need to find it. Here, I ask you to use 2 different methods to find that point, that line. Okay? First, through formula calculation. Fibonacci numbers. We have the Fibonacci formula. Can you use the Fibonacci formula to calculate, to find that number? Method 1. Yeah. Because it is not complicated. So let me explain the formula here. First, let's recall what is the Fibonacci formula. Fn 1 over root 5 parenthesis phi to the n minus negative 1 to the n over phi to the n. Right? Yeah, that's the formula. Exact. This formula is exact, not approximation. Exact. Here the question. Because when we plug in the n number, we need to see at what point the function returns the number just past the overflow line. Okay? Yeah. Overflow line, what is the overflow line? Right? Yeah. Because we use long integer. Now here, I use Java as an example. Okay? Not Python. Python, the story is different. All right. So in Java, we use long integer. Data type. Long integer, we know 64-bit integer, right? Each integer, we use 64-bit integer. Then, there is a specific largest long integer number, right? You can calculate, okay? Something like 2 to the 23rd, 63rd, not 23rd. Why not 64, 64th, 63rd? Why not? Remember, sign bit, the first bit cannot be used to represent number. Okay? Here, I didn't say unsigned. If you consider unsigned, then you can use 64 bits, all for numbers. Here, there is a signed bit that cannot be used. Okay? So we skip the signed bit. Right. So that means this number, right? But this number you do not need to calculate. In Java, there is a constant. Long, max, long, some constant. You just, in Java, you just, call that, access that constant. Okay? Here, I couldn't remember the name of the constant. So when you search the web, you can find that constant easily. Okay? Copy, paste. Here, let me just use this, L max of that. I refer to that constant. Okay? The largest long integer number. Right? Here, we need to solve this inequality for what n the Fibonacci formula returns a number, integer, that barely greater than this largest long integer. Barely greater than that. Okay? Yes. Yes. All right. Yeah. Yeah. But you can see, if you want to solve this inequality directly, it is not easy, right? Yeah, because exponential function, you have two terms. It won't be very easy. Yes. Fortunately, we can take advantage of this special structure of the formula. This formula has a very special structure, so we can take advantage of it. Take advantage of it. Okay? Yeah. All right. So here, let me do some formula transformation. Important formula transformations here. So I just use the space here. Not much space. All right. First step, easy. Multiply root 5 both sides. V to the n minus root 5 L max. Here, one question. When you do computation here, use the double data type. Use double data type. Okay? That means this long integer, you need to convert it to the double. So it's easy. Yeah. So when you do computation, because root 5 is double, okay? Double multiply integer, you will get double. Okay? Yeah. The reason using double, we know the range for double data type is much larger than integer range. Integer range, you get an overflow quickly, but when you move to the double, you don't worry. Yeah. So, near that point, because, range is huge. Okay? Range is huge. But there is a limit. But the difference is huge difference. So you should not worry about the overflow for the double at this point. Okay? You are safe. All right. Then look at this part. How large is this part? The numerator plus or minus 1. So absolute value of the numerator is 1. How large is the denominator? When n is large, denominator extremely large, right? V to the n. If the denominator is extremely large, is it close to 0? So this number is close to 0. Extremely close to 0. All right? So then our inequality becomes phi to the n plus that little term, right? Yeah. But so here the question. We like to drop it. Okay, because extremely close to 0, we like to drop it. But remember, if you drop it, we don't want to miss any critical integer. If you drop it, there is a very small chance you may miss one integer number. We don't want that happen. We don't want that happen. All right? Even a so small little integer, or not integer, number, real number. We want to, in other words, if you want to drop, we want to drop it in a safe way. How about that? Not a dangerous way. Right? You drop something, what do you mean safe way, dangerous way? If you drop something, although it is small, but it is at a critical point, that is dangerous. We want to drop something not at a critical point, okay? Yeah? Not at a critical point. So here, how about, let's modify this inequality here in a more generous way. How about that? More generous way. More generous. Okay? So what do you mean more generous? Actually, we do not drop it. How about we increase it a little bit? Then give us some room, right? Yeah. So the part we increase should cover the small difference. That's the idea. Okay? So here, that means we can do things more generous, but not short. Okay? Not short a little bit. Short a tiny bit. That could be dangerous. So we don't want that to happen. Okay? How about we consider another inequality, but a more generous inequality. Let me carry it this way. Phi to the n greater or equal to root 5 times L max plus 0.1. How about that? Is that 0.1 much bigger than that? Much bigger than whatever it is, this term. Yeah, 0.1. So we replace that complicated term. That is a complicated term. But after we do this kind of replacement, we make the right-hand side larger, right? That means if our n is greater than this one, definitely it is greater than the previous one, right? Because that's what I mean, more generous. That's what's more generous here, all right? Yeah. Here, the right-hand side, just a plain number, right? No variable. All known numbers, right? Yeah. Can you solve f for the left-hand side? Okay. Yeah. You can take natural log, whatever log it is. Okay. So here, let me take natural log. N times natural log phi greater or equal to natural log of root 5 L max plus 0.1. Then find n greater or equal to ln root 5 L max plus 0.1 over natural log phi. Okay? N greater or equal to that number, and we know, and we should take, because and here, that NO. So here, let me see. All right. Yeah. Remember, I used notation NO before, right? NO, because this NO corresponds to overflow. When overflow occurs, that means NO is a bad one, right? Bad one corresponds to overflow. Good one does not correspond to overflow, right? Yeah. So here, for this formula, we can use to find the largest good one. Largest good one. Okay? Yeah. Not the bad one. So that we may call N max. All right. N max. The largest good one before the overflow. Before the overflow. So how about we take floor function? Because it should be an integer, not city function. City function it will be NO. Okay? So floor function. Then that long formula okay, floor function. So that one. Our method one, you can see here, I give you the exact formula, how to calculate the largest size if we use the long integer data type. When you hit this one, you're fine, but after you increase this number just by 1, you get overflow. You get overflow. Right? Here, I can tell you the answer. So based on our previous experiments, I can tell you the answer. The answer, this number is 92. Not very big, only 92. That means 92 you're fine. 93 you get overflow. 93 you get overflow. So that means how limited, if you use long integer, how limited the calculation you can do. Not too big. Fibonacci number after 92, you cannot do it right. You cannot do it right. Okay? So that's the reason we choose the big integer. So you never need to worry about overflow problem. Okay? Imagine 10,000. Nothing. Okay? 10,000. No problem. Okay? All right. So I added this overflow part. So here you have another round experience to understand overflow better. Remember, in the first project, you have some experience understand overflow. Here, try to understand better. Okay, all right. Yeah, that's method one. I hope you can follow the derivation of this math formula. Yeah. For some students, probably very involved. Try to understand how the logic. So we have the video, so you can watch a few times. All right. Method number two, find this number using some special property of the overflow. Special property. Here, the first method we use mathematical way. That's the mathematical way. All right. But the second way we use the computer science. Not from math formula, computer science. In the computer science, so here, there is a special method. After you calculate the Fibonacci, how do you know you get overflow or not? So there is one detection method that can tell you if your computation is correct. Remember, Fibonacci number, you need to do the calculation. Fn equals Fn minus 1 plus Fn minus 2. When you do this addition, does it give you the correct answer? That's related to the overflow. If you hit overflow, it does not give you the correct answer. Right? If you do not have overflow, then you get a correct answer. So you need to call some special method to tell you if this addition returns correct value or not. Okay? So there is a method. So here I give you the keyword you can search. Exact. If the answer you find is exact or not, that keyword will give you the appropriate method you can use to tell you correct or not. Okay? So you try both methods, you should get the same answer. Same answer. Find the overflow of that line. Okay? That line. Hopefully, after this round, understand. So you get a very good, awareness of overflow problem. Otherwise, when you solve real-world problems, you may not be aware of it, right? You may not be aware of it. You just do it in the normal way, but at the end, you may get a wrong answer. Sometimes ridiculous answer. For example, you calculate the Fibonacci number, you get a negative number. How about that? It returns a negative number. Why negative? Remember the sign bit? I mentioned the sign bit. If the sign bit is 1, it's negative. When sign bit is 0, you get a positive. Sign bit is 1, you get negative. So your Fibonacci number becomes a negative number. How ridiculous it is. Right? Do not make, so here, although the problem I'm talking about, it looks like not a big problem, but think about it. If, when you work in the real world situation, you work on a project, provide your customer solution, and the solution are expected to be positive numbers, positive integers, but based on your algorithm, if your customer receives your solution and run it, sometimes it returns a negative, then your customer will be mad, right? Because it must be 100% wrong. You provide a negative number, right? It must be 100% wrong. So your customer will be very mad. Think about that situation. That means you didn't realize, you may not realize the overflow problem. Okay, you ignore the overflow problem. You just do the straightforward calculation. You ignore the overflow problem. But your customer, they need to work on the real world problem. Fibonacci, when they plug in 93, negative. Then they will be mad. they will ask for refund, right? That's the here. So I just want to give you some real world scenario, how dangerous it could be. Okay? The overflow problem could be. So after this class, you really need to never forget this overflow problem. Okay? Never. It's mainly for integer. For other data type, although there is possibility, but that happens not that easy. For integer computation, it could happen very easy. Very easy. N equals 93, you get over. So mainly for integer computation, always think about overflow ratio. All right, let me move to the next topic. I already spent too much time. All right, next, you just read the instructions, but here I want to talk about the optional part. I also give you some optional subproblem. Let me call subproblem. You can earn up to 3% extra credit. That's quite a lot. Because this method is very interesting. You need to apply new knowledge to solve it. Yeah? For some students, if you have extra energy, you can try to solve it this way. This way, the goal, let me tell you the goal. The goal, this algorithm, you can find the Fibonacci number in log n. Faster than our previous one. Our previous one is n, right? Here, log n. Much faster. That's interesting. How to get a log algorithm based on this nice matrix formula. Someone discovered this matrix formula, very smart. I don't know who discovered it. Okay? Probably more than 100 years ago. Okay? But we can prove it easily. We can prove it easily. But the one who discovered it, that's huge. Using this formula, we can calculate Fibonacci number in big theta of log n. Much faster. Okay? Here, let me stop right here because this is optional one, not for everyone. Right? Usually for 1/3 of the students. So I plan to use videos to explain furthermore. Okay? If you do not plan to do it, you just ignore the videos. Okay? In the videos, I will explain, the whole story. The whole story. Okay? All right? Because I want to move to the next topic. Any question if I move to the next topic? All right. Next topic, problem solving. Remember I mentioned there are two important problems. Very challenging, very interesting. So here I use this time, less than half an hour. Less than half an hour. I try my best to complete these two problems. All right. So next topic. P.2, find 5-element median. I mentioned many times, but here, I want to tell you the solution. Find 5-element median in 6 comparisons. 6 comparisons. So let me show you how to do it. All right. And this question, actually, we are almost there. I don't know if you realize it or not. because I already split this problem several places. Homework assignment 1 and the midterm test. Several places, a few pieces. Now you only need to connect the dots. Then you get an answer. I don't know. So if you realize it or not, here I just point those dots, critical dots out. All right. Read that. So the first thing, right? So when we start, we have 5 elements. Okay? I use x1, x2, x3, x4, x5. These 5. First, we need to do some comparisons to get started. But at the beginning, how to choose comparisons? Not that important, because at the beginning we know nothing, so we have a lot of freedom. Okay? So let's group these elements in these 2 pairs. x5, no pair with it. Okay? So first 2 pairs. Right? So the first round comparison number 1, comparison number 2, we can assume the winner is x1, the winner is x3. Okay? That's the first comparison. All right. Then, the second comparison. Here, then x1 here, x3 here. Second one, all right? Comparison number 3. Number 3. So we can assume the winner is x1. Sometimes we can assume, sometimes we cannot assume. Here, I want to mention this because suppose you have 2 cases. The cases are symmetric. If you flip, no big difference. For example, for this comparison, x1, x2, which one is larger, which one is smaller? Not really big difference. x2 could be larger, x1 could be larger, but if you flip, then the 2 cases are symmetric, right? Here I say symmetric. Okay? You can flip to convert one case to the other. Okay? So in this situation, you can assume one is larger. Okay? If not symmetric, if you flip, the situation is different, then you cannot assume. Okay? Yeah. When I do grading, some students, when there is no symmetry between 2 cases, they still assume. That's wrong. Right? But here we are safe to assume one is larger because 2 cases symmetric. Okay? Here, x1 or x3, which one is larger? 2 cases symmetric. Okay? Symmetric. It's essentially the same. All right? Yeah. After these 3 comparisons, let us interpret our data. Because we collect some information, we want to see the picture better. Before we do comparison number 4, we want to do some cleanup work. We want to see some special structure in our data. Here I use a diagram to show you the picture visually. All right. The larger the element I put on top, okay? Because x1 is larger than 3 elements, right? So I put on top. x1 is larger than x3. x3 below x1. Okay? But x3 is larger than x4, right? So I draw this diagram. So you can see visually, easily, oh, which one is larger, which one is smaller. Another one, relationship with x1. x2 is here. So that's the picture diagram we have after first 3 comparisons. Okay? I will go 6 comparisons. Go 6 comparisons. So 3 comparisons to go. Okay? All right. Before we do the comparison number 4, do one critical step I gave you in one of our homework questions. Do you still remember? Here, x5. In homework question, x1. Yeah, I don't know I use greater or smaller, but basically it's the same. x1 greater than x3, greater than x4, and x1 also greater than x2. I ask you which element can be eliminated from consideration for a median. Remember that question? Our answer is x1. Because the only element that x1 can be smaller, that's x5. So x1 can only be the first largest or second largest, right? That's the only possibility. x1, largest or second largest. But none of them could be the median, right? x1, so here, only 2 possibilities. Largest or second largest. But both of them not equal to the median. Can we remove it for consideration? Right? Yeah. Yeah. Our elimination method. Remember our elimination method. If some elements have nothing to do with the median, why we keep them? Right? So you can see how important is the elimination method. By the elimination method. Okay? x1 can be removed from consideration. Then we simplify the situation. After that step, we have x2 here, and we have x3. This line, we keep it, right? Because the information of this link is important, useful, right? Then, we have x5 here. Then, let's update. How do we interpret the median, original median?
Second largest?
Correct. What I mean original. Because after we move that one, what would be the equal to the second largest? In these 4 elements. Did I give you many questions related to the second largest? Think about in homework assignment, midterm, right? Yeah. One question, I break it. Remember, I give you x1 less than x2, x3 less than x4. I ask you, how many more comparisons do you need to find the second largest? Do you remember that? 2 more. Okay? For the worst case, many students give me 1 for the best case. Okay? 1 is for the best case. Yeah. I agree. Yeah. But we always get the worst case. 2 for the worst case. Can we apply here? Right? Here. Oh, I also give you another question. I didn't give you these two inequalities. I asked you find second largest directly in the midterm, right? Remember? The answer is 4 comparisons. Without these two, because we need to do 2 comparisons to get these 2 inequalities. Without these two, 4 comparisons. Right? But here we have 1 of them, not 2, right? We have 1 of them, right? So the first comparison we should compare 2 and 5. So that's comparison number 4. Other than comparison number 4, other than that, remaining, do you know how to, the larger you get the largest with 1 comparison. After comparison number 4, number 5, compare 2 larger ones. Okay? The larger one would be the largest, right? Not the second largest. So the largest one won't be the winner, let's say. The winner won't be the solution because the winner is the largest one of the 4. Okay? We don't need the largest one. We need the second largest one. Okay? So the loser compare the loser with what? Yeah. All right, so here, we can assume, all right, here, because also quite symmetric. Quite symmetric. Let's assume here, x to x5, x2 larger than x5. Okay? X3 larger. Because in order to make our discussion easier, we can assume a little more. All right? Suppose x3 is the winner. Okay? X3 is winner. Loser, x2. So there you should compare x2 with x4. Okay? Loser, so here x2 with x4. The winner would be the second largest. Winner would be the second largest. Okay? All right. So here you can see 6 comparisons. 6 comparisons. All right. Yeah. But after this question, you can see after this question, we did one question that find the second largest among 4 elements. I also like to give you the solution for a more general question. Find the second largest element in an n-element array. This question, not very complicated, but also very interesting. But today, because I do not have much time left, I only have a little more than 10 minutes. So today I want to skip this one. Okay? I hope later at some time, for example, in the review for the final, I can give you a solution of this one. Well, we do review for our final exam. So let me use the remaining about 10 minutes to solve that next problem. sort 5-element array. Another important question for this class. So I feel these two questions, the previous one, find the median of 5 elements, and this one, after you take this class, you need to know how to solve these two. That will lift you the level to certain, good level. Otherwise, after you finish this class, you do not know how to find the median of 5 in the best way, and how to sort 5-element array in the fastest way. That's not good. Okay? That's not good. All right, so let me give you the solution. Because I only have 10 minutes, so I try to shorten my explanation. First 3 comparisons. No nonsense, just a copy the first 3 comparisons from the median problem. Same? So, first 3. First 3 comparisons. Same as that median one. Here, let me just draw a picture. Okay? X1, X2, X3, X4. Suppose X1 first round winner, X3 first round winner. Another comparison, 1, 2, 3, X1 second round winner. So after 3 comparisons, the diagram here, I repeat the same diagram that we had before. We set this as our starting point. How about that? Yeah. Because when we develop our knowledge, we always build up on our existing knowledge base, right? Yeah. We never want to invent the wheels, right? Yeah. Yeah. So that's important. Yeah, because I noticed some students, when they work on the midterm problems, they start from scratch. Actually, you have very thick base. You can use directly, right? Why you start from scratch? Okay? Here, we don't start from scratch. Yeah. We already have this good base to start with. Okay? All right. Then, look at comparison number 4 regarding X5. Can you tell me, because we need to use X5 to compare one of the first 4 elements. Can you tell me which one is the best one to be used to compare with X5? X1. X1. Why X1?
Because it's a maximum now.
Maximum? Or any other suggestion? Hey, you need to use some reason based on your previous knowledge. Your old knowledge could be borrowed. Borrow from binary search. Binary search. Connect to binary search. How do you do comparison in the binary search? Ignore X2. How do you do the binary search? X2 is the distraction. Okay? You cover X2. Can you connect to binary search? This is a sorted array, right? Ordered array. Which one you do the comparison? The one in the middle. Always do the one in the middle because that's the most efficient comparison. So this is comparison number 4. Okay? After this comparison, then there are 2 possibilities, right? X5 greater than X3, X5 less than X3, and these 2 cases are not symmetric. You cannot assume, okay, this time you cannot assume X5 greater than X3. So you need to do discussion on both cases. Only when you have symmetric cases, you can pick one of the two. You save you one half of the time. But here, clearly, not symmetric, right? The picture also not symmetric. Okay, all right. So we consider case one, that should be like this. X1, X2, X3, X4, X5 is here. Okay, all right. Case 2, X3, X4, X5 is here. Okay? These two diagrams. Okay? So I do not need to write a lot of words. Okay? I just draw figures. Okay? Next, anyone can give me some idea how to do the next comparison number 5. Comparison number 5. We try to, organize our data, make it closer and closer to be ordered to that destination. Which one you think? I need to control my time. All right? We have enough time. Okay? At least 5 minutes. It should be enough. The last few steps. All right. Think about this, because we have some part of data get ordered, almost ordered, right? Yeah. If you do one comparison between X1 and X5, can you extend the ordered part of the array a little more, right? X1 and X5. So use your imagination. In our mind, our human brain, so we can do a lot of nice imagination. So use that. Okay? Yeah. Here, because our goal to get all the elements in order, so that's our destination. When we do comparison, we move toward that goal. Okay? Here, comparison number 5. Number 5. Yeah, let me use parentheses. X5 and X1 and X5. Okay? After that, there are 2 possibilities, right? Yeah. But if I draw 2 possibilities, that could be, maybe a lot of discussion, right? So here, all right, I want to save some time. Okay? There are 2 possibilities. Which one is worse? Let's just work on the worst. Remember, we always want to solve the worst case. X5 is greater, it's worse, or X5 is smaller, worse. Relatively worse. Which one worse?
It's smaller.
Good. X5 smaller, worse. That's it. Yeah. That's it. Can you explain to your classmates why you feel it's smaller?
Because if it's greater, then you're going to have a straight line up. So you're going to have X4 is less than X3 is less than X1 is less than X5.
Yeah.
But if it's less than, then you're not going to really know where it plays in X2 or X3.
Good. Yeah. Let me draw that diagram. Good. 4 minutes. All right. So use the worst case based on the adversary argument. Adversary will give us the worst one. Okay. So that would be X1, X5, X3, X4, and X2 here. The reason this is worse, think about it. If X5 is higher, then for the remaining work, X2 only need to worry about 2 elements. If X5 below X1, X2 need to compare with 3 elements. 3 is worse than 2, right? 3, you need to do more work than 2, right? So that's why the adversary will give us more work to do, not less work to do. Okay? That's the reason. That's the reason. Okay, adversary argument. Very good one. Try to use it. Okay? Alright. Then the next two is easy. Binary search, right? Yeah. Number, comparing the middle, number 6. Bigger, smaller, just one more, number 7. Okay? Number 7. Binary search. Okay, so. Okay? Alright. This one, I think similar. Idea similar. Yeah. This one actually is symmetric. X5, here if you compare X4 and X5, the result is symmetric. Right? Yeah. Here, because I still have 2 minutes, so let me just complete it. Although some of you already see the solution, let me just complete it. Okay? Number 4, X4, X5, and the diagram we can assume, so here, because X5 or X4, which one is larger, symmetric, okay? X2 here, X2 here. Now the boundary search number 5, yeah, this is number 5, okay? So number 6, sorry, this is number 6. Last one, the boundary search 7, okay? Worst case 7. All right, yeah. Quite complicated, but if you follow the logic, the story, yeah, connecting many dots, do a lot of imaginations, you can get it. Okay? You can get it. All right. Yeah. Yeah. Try to understand these two solutions as much as you can. In the final, I will put a few questions related to these two. Okay? Because these two are so important for this class. So I hope you understand really well on these two questions. All right, that's it.